All right, so now that we have our OLS down, what we want to really focus on and reiterate is the importance of the distinction between the model and the sample. So here's the model of the population. Y equals beta naught plus beta 1 x plus u. This is the true representation or the true relationship between y and x. The problem here is we don't see every y and x for the population. We don't actually estimate beta naught and beta 1 for the population because we don't have everyone. What we have is a random sample or a sample. And so our sample estimation is we take that same y and now we get beta naught hat plus beta 1 hat x. Our u's drop out because we're just doing that best fit line of the data. Now, one important part about this is what we want the expected value of beta 1 hat to equal beta 1. That is, we want beta 1 hat to be unbiased. That's the key. All right, now this might be, you have to go back and review in statistics the details of that, but that's what we want to be able to accomplish. Is that if we take the expectation of beta 1 hat, it equals beta 1. And so there's 5 assumptions that we need to satisfy in order to ensure that this is the case. Assumption number 1 is we need to be linear in parameters. Well, we know y and x are our variables, and so beta naught and beta 1 are our parameters. They need to be linear, meaning they need to be beta naught and beta 1 by itself. What we cannot have is y equals beta naught plus beta 1 squared x plus u. This is bad, and this would violate the linear in parameters. That is not linear. That's bad. We could have y equals beta naught plus beta 1 x squared plus u. This is linear in parameters. This is good. Second assumption is random sampling. We need to make sure that the individuals that we observe, individuals that are part of our y and our x, are chosen randomly from the population. For example, if I want to know what's the relationship between education and wages, and all I do is ask SUU graduates, that's not a random sample of the entire US population. All right, so I need random sampling. Third is called zero conditional mean. And what this means is if I take the expected value of y conditioned on x, I should get exactly what I want. So this is expected value of u conditioned on x is equal to 0. And the reason we do that is we do the expected value of y conditioned on x. This is equal to, well, now I'm going to substitute in what y is with this. The expected value of beta naught plus beta 1x plus u conditioned on x. Meaning that if I know x, what do I expect y to be? So if I'm rolling 2 dice and I want to know my outcome is the summation of the 2 numbers on the dice. I roll that first one, I say, hey look, the first dice says 6. What do I expect the summation of the 2 to be? Well, knowing what x is, what one of the dice says, it gives me information about what the summation of the 2 are. So this can then be rewritten as the expected value of beta naught conditioned on x plus the expected value of beta 1x conditioned on x plus expected value of u conditioned on x. Okay, well, expected value of beta naught conditioned on x is equal to beta naught plus, or not beta naught hat, that's my expected value. Expected value of beta 1 is going to be beta 1 hat. X conditional on x is just x plus, and now there's this error term, but we are assuming that's 0, so that's plus 0. So now the expected value of y conditional on x is equal to our best fit line. And that's what this assumption needs to do for us. Fourth is sample variation. You need to have different y's and different x's. I can't just ask one person a question, find out what their wages are, what their education is, and then multiply that by 2,000 and say I have 2,000 observations. I need unique observations that have variation in both y and x. And fifth, so we can get this on there without crashing things. Fifth is what we call this is a big word, dasticity. That will win you any Scrabble game that you play. And what this is the variance of u, condition on x, is a constant, sigma squared. Okay, now if you want more detail on this, you're going to have to look in the econometrics textbook or Google it, but it's beyond the scope of this class. But these are our 5 assumptions. If these are true, then our expected value of beta 1 hat is equal to beta 1. Now, full disclosure, linear parameters, not hard to do. Random sampling is challenging, but we can overcome some of that. Sample variation, not a problem. Homoscedasticity, easily correctable. This is the beast. And so we'll talk a little more detail about how do we satisfy that, but it's going to be a little more challenging, and it's going to lead us to want to do what's called multivariate regression, and not just have one x, but can we include multiple x's in our estimation and in our model.